The conditional probability of A given B is the probability of event A given that B has occurred. To explain this, let's start by finding the probability of an event A. Here's our event and here's our sample space. If I want to know the probability that event A occurs, I'm going to say, well, it's the probability of A, or the number of items that were in A, out of the probability of your sample space, or the number of items that were in your sample space. So you're taking this region and dividing by everything outside of that region. Now let's say that I have some additional information that can break up the sample space, and everything on this side belongs to event B. And if B does not occur, that's the complement. It's everything on the right-hand side. So if I want to find the probability of A, knowing ahead of time that event B occurs, I can look at a new diagram. Pulling just the B portion of this diagram and just the portion of A that's within B, I get this half of the picture. So to get the probability of A given B, I'm going to find the number that's in both. The probability of A intersected with B. And then I'm going to divide by the new sample space, which would be the entire box, or the probability of B. This is your formula to calculate conditional probabilities. Every woman over 40 should have a mammogram yearly. If a primary relative has had breast cancer, you should have a mammogram at an age 10 years younger than that relative was when diagnosed. Here's why. Breast cancer is the second most frequently diagnosed cancer in women. A woman born in the United States has a 38.97% chance of developing cancer in her lifetime. Let's assign some notation here. The probability that a woman develops cancer as a decimal is 0.3897. Based on current incidence rates, the chance a woman born in the United States will never have breast cancer is 87.6%. We're basically saying the probability that you do not have breast cancer, so the cancer and breast cancer did not happen, is 0.876. If you want to find the probability that a woman could have breast cancer or does have breast cancer, you would use complement rule. So the probability a woman has cancer and it turned out to be breast cancer is 1 minus. Remember that complement, you switch it to a 1 minus to get rid of it. 0.876. So the probability a woman will get breast cancer is 0.124. Stacy just learned she has been diagnosed with cancer. So we know this ahead of time. Stacy knows for a fact she has cancer. That goes in the given position. Whatever you know ahead of time, you put after the slash. What is the probability she has breast cancer? We're going to apply the formula. It says form the intersection of the two events and then divide by the given event. So in the numerator, I'm basically looking for the probability the woman has cancer and that cancer is a breast cancer. Well, we already found that. That's right here, 0.124. And in the denominator, I just want to find what's the probability the woman will get any form of cancer in her lifetime. And that's 0.3897. So if you divide these two numbers out, you'll get back 0.318. Given that a randomly selected roper has damaged fingers, so we know ahead of time, whatever you know ahead of time you put in this position, has damaged fingers. Well, let's see, the symbol for that is D. What is the probability that the roper is a healer? And in terms of notation, healer, that's H. So if I apply the formula, it says find the probability of the intersection divided by the given. So probably being a healer with damaged fingers, that's 23 people out of 256. And then the probability of damaged fingers, that's 23 headers plus 44 healers for a total of 67 people with damaged fingers out of 256. In these fractions, the 256 cancels out and you get back 23 out of 67. Now there's a shortcut to working these problems. Let's go back and reread this. It says, given the roper has damaged fingers. So we know ahead of time, anyone with an undamaged finger is gone. Anyone missing a finger is gone. For us, the only thing that exists is damaged fingers. So this total of 256 is gone. Our new total is 67. So when we find a probability, we're looking out of 67 people, only people with damaged fingers. Now, out of these 67, how many of them were healers? Well, 44. So you can cut through the formula. You can skip all of this and just jump straight to your answer on problems with contingency tables. It is estimated that roughly 39% of the population still hunts and 34% of the population dog hunts. Let's assign some notation. So we have the probability of still hunting is 0.39 and the probability of dog hunting is 0.34. Many still hunters view dog hunting as disturbing to the wildlife. Many dog hunters view still hunting as boring because there's not a need to train dogs or drive fast to cut off dogs. Assume 60% of the population still hunts or dog hunts. And remember that keyword or? That's why I put a union in between the still and the dog. So part A, what is the probability that a randomly selected hunter both and still hunts and dog hunts? Well, to answer part A, I'm going to go back to this formula, the probability of A union B. So the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. And in this formula, let's replace A with still hunting and let's replace B with D for dog hunting. So now I can come and plug numbers in. The probability that you still hunt or dog hunt, well, that was told to us, it's 60%. And the probability of still hunting is 0.39. The probability of dog hunting is 0.34. And now I can subtract off the probability of doing both. If you come in here and solve this formula, add the probability to the left-hand side, and then subtract off the 60%. You'll get back 0.13 for your answer. So the answer to part A is 0.13. 13% of people do both. In part B, I want to know what is the probability that a randomly selected person neither. So they are not going to do whatever this thing is saying. So they neither still hunt nor dog hunt. And when you see the word nor, this is the same key word as the word or. And to work this out, you need to get rid of the complement. And the way you eliminate it is 1 minus the probability that it does happen. And the probability of a still hunting or dog hunting is 0.6. So if I plug this in, 1 minus 0.6, there's a 40% chance that someone's not going to do either one. In part C, we want to find the probability that a randomly selected person still hunts given that they dog hunt. To work this out, let's apply the formula. We need the probability that they dog hunt and still hunt, and then divide it by the probability that they dog hunt. Well, doing both, dog hunt and still hunt, that's what we found in part A. That's 0.13. And the probability that they dog hunt, well, that's from the problem itself. That's 0.34. And if you divide these two numbers out, that'll give back 0.38. There's one last thing we could do with this problem, and that's to draw a Venn diagram of the situation. Let's say that these are all of our still hunters and these are all of our dog hunters. When you're labeling a Venn diagram, the first thing you want to do is start by labeling the intersection. So we need people who still hunt and dog hunt. And that's what we found in part A of the problem. It's 0.13. So we'll start by putting 13% in the center. Now if you're looking at the still hunting circle, the still hunting circle is composed of people who only still hunt plus people who still hunt and dog hunt. If you're looking at the probability of still hunting of 0.39, Out of the 0.39, you have to subtract off the 13% who also dog hunt. So I'm doing 0.39 minus 0.13, and that gives back 0.26. That's the number that goes here. So 0.26 plus 0.13 gives the total of 0.39 who still hunt. Next, let's look at the dog hunting circle. In the dog hunting circle, we know there's 34 total, but out of those 34%, 13 of them also still hunt. So if we subtract 0.34 minus 0.13, that's 0.21. So 0.21 only dog hunt. And if you take all three of these numbers and add them up, that adds to the 60%, the value that's in all three circles. So if you want to know how many do not still hunt nor dog hunt, part B, you're basically saying what's the probability of being somewhere out here, outside of these two circles. And to get that, you could do 1 minus the 60%. That means there's 40% left over who don't dog hunt or still hunt. These are the works cited for this lecture.